Hello all. In this lecture, we'll discuss what is alpha decay and the theory of alpha decay. Alpha decay generally happens in nuclei which have more than say 210 nucleons and which are very large in size. When nuclei happen to be large in size, what happens is that the short range nuclear forces are not able to overcome the mutual repulsion between nucleons. So they tend to be a little bit unstable. And to attain stability, they have to reduce their size so that nuclear forces are in control and they are greater than the Coulombic repulsive forces. So, for easy attainment of size reduction and stability, nuclei undergo alpha decay. For alpha decay to occur, generally the kinetic energy of alpha particles should be large enough. Now, why are we saying so? Because in the whole theory of alpha decay, the concept is that alpha particle is already preformed inside the nucleus. And for the alpha particle to come out of the nucleus, it has to overcome the barrier offered by the nuclear forces. So, in order to overcome the barrier offered by nuclear forces, generally the produced alpha particles should have sufficient kinetic energy to overcome this barrier. For any nuclear reaction, we can define something called Q value of a reaction. Just imagine a reaction where uh, a parent nucleus, say an initial nucleus, uh, gets converted into, say, Y and an alpha particle. So, this is your initial nucleus with mass Mi, and this is your final daughter nucleus with mass Mf, and your alpha particle mass, that is what we have taken as X, Mx. Okay. So, if this is the case of any nuclear reaction, then the Q value of a reaction is the difference in mass energies of initial nuclei and the products. So, this is what we define as Q value of any reaction. This is true not only for decay but for any sort of nuclear reaction. We can define something called Q value. By the conservation of energy, the mass energy and kinetic energy of the initial parent nucleus should be equal to mass energies and kinetic energies of the final product daughter nuclei as well as the outgoing particle. Here in this case it's the alpha particle when we are talking about alpha decay. So you can imagine the picture as something like this. You have a nuclei which is at rest. So the kinetic energy is 0. Here T's are the kinetic energies and MC squares are the rest mass energies. So just consider that the parent nucleus is at rest. So its kinetic energy is 0. And you have a daughter nucleus as well as an alpha particle being produced. And for conservation of linear momentum, they have to go in the opposite directions. That is there. But the daughter nucleus is quite heavy, so it doesn't take much of the kinetic energy and it doesn't move much. But the alpha particle is lighter, so it takes up most of the kinetic energy. And it's you can also write this like this, because Ti is 0 on your left hand side, you just have mic square, and on the right hand side you have all these terms, and if you take the difference of mass energies, this is what you get. This is also equal to the kinetic energy of alpha particle and kinetic energy of the daughter nucleus. And the daughter nucleus doesn't take up much of the kinetic energy, and it's very easy to show that most of the energy produced in the reaction, the difference between mass energies, is the energy that is being produced in the reaction, and this energy is mostly taken up as the kinetic energy of the products. And in the products, the daughter nucleus doesn't take up much of the kinetic energy, so almost 98% of Q value is taken up as the kinetic energy of alpha particle, and it's very easy to show that, because generally we said that nuclei which have nucleons greater than 210 undergo alpha decay. So if it is so, just plug in such high A values and you can see that this fraction counts to be nearly 98 percentage. Now, in the case of alpha decay, uh, theory has been proposed which is called tunnel theory of alpha decay. Now, why is it that we need such a theory to explain the process of alpha decay? We'll see that. If we plot the potential energy of an alpha particle as a function of distance from the center of a certain heavy nucleus, that nucleus is unstable, and we are just imagining that the alpha particle is formed inside the nucleus and it is trying to come out of the heavy nucleus. So we are just plotting the potential energy of the alpha particle with distance from the center of a heavy nucleus. This is what it looks like. So this is the potential energy of an alpha particle with respect to distance from the center of the nucleus, which is marked as 0. So as long as the alpha particle is within the nucleus, it is inside a potential well which has a certain depth, and the alpha particle is bound by nuclear forces. But then beyond the range of nuclear forces, the alpha particle will be facing Coulombic interaction. Okay, so that is where the nuclear potential falls down, and that is what we have depicted here. So this is the potential energy of the alpha particle. And here you can see that there is a potential barrier of about 25 MeV. There is a potential barrier of about 25 MeV, and this potential barrier just tells you that if you are bringing an alpha particle from infinity to this position, it will be facing such an opposition, this much of an opposition from the nucleons within the nucleus. So you have to do that much amount of work to place an alpha particle from infinity to this position in the range of nuclear forces. So for an alpha particle which is inside the nucleus, for it to come out of the nucleus, it will again have to cross a barrier of height 25 MeV. According to classical physics, if a particle has to come out of this well, if a particle is within this well and if it has to come out, it has to jump over this barrier and come outside. But to jump outside, it must have energies greater than 25 MeV, isn't it? But the energies of alpha particle inside the nucleus, they are not that much, and they are just in the range of say 4 to 9 MeV. Okay, so it is like say this 16 or 20 MeV short of the energy needed for escape. To escape, it requires 25 MeV, but its energy is only just 4 to 9 MeV. So it requires more amount of energy to come out of this, to cross this barrier. So classically, the alpha particle has no chance of overcoming this barrier. And this is where we seek the help of quantum mechanics, where we talk about a phenomenon called tunneling, where particles can cross this barrier. Particles whose energy is less than the barrier height can just tunnel through the barrier and can be found outside. So This is how we explain how the alpha particle comes out. So the basic notions of the theory that was proposed by Gamow was that alpha particle is an entity that may exist within a heavy nucleus, and this alpha particle which is inside the nucleus, it is in a state of constant motion, and it is just you can just imagine this barrier as some wall, and the alpha particle is constantly coming and hitting this wall. It is in a state of random motion. It is going from here to here. It is hitting this wall. It is going to the other side. It is hitting there, and it is in a state of random motion, and in a state of constant motion, and it's constantly hitting this wall. And there is a definite, even though small, there is a definite likelihood that the particle may tunnel through the barrier, even though the barrier height is much high and the alpha particle doesn't have enough energy to surmount the barrier. So each time a collision occurs, there is a definite small probability for the particle to tunnel through the barrier. Now, according to the last assumption that we made in this theory, let's assume that the decay probability per unit time is lambda, and if we are thinking of the alpha particle as pounding the barrier new number of times per second, that is, you can just imagine the picture like this. You have a nucleus, spherical nucleus, and a small alpha particle is there in the within the nucleus, and it's just constantly hitting the walls of the nucleus, and it's trying to escape from the nuclear forces. Okay, so if it hits new number of times per second, and for each hit, let T be the probability that the particle will be transmitted through the barrier, then the decay probability per unit time will be nu times T. Now, just imagine that the radius of the nucleus is R0. If so, the diameter would be 2R0, and that is the distance that the alpha particle can travel within the nucleus, maximum distance, isn't it? And if v is the velocity with which alpha particle travels, then the collision frequency nu can be written as velocity by distance. Okay. And if we plug in the typical values of v and r naught, we see that the collision frequency is as high as 10 raised to 21 per second, which means per second the alpha particle is colliding with the walls 10 raised to 21 times. And if you look at the it's such a high frequency, so this much number of times the alpha particle is hitting the walls of the nucleus. But still, if you look at the half-life with which alpha particles are produced from the nucleus, you see that it takes such a large amount of time to escape from some nucleus, say like 10 raised to 10 years to come out of a nucleus. Even though it's trying hard, it's not able to come out of the nucleus quickly. That's what we should understand from this value. So the picture in the point of view of quantum mechanics would be something like this. You have a nucleus of radius r naught. The alpha particle has an energy E, kinetic energy E, but that's not enough to surmount this barrier. And this is the potential energy of the alpha particle that has been depicted. And you see that at this point, at this particular distance, the kinetic energy of the alpha particle and the potential energy of the alpha particle happen to be the same. And beyond this point, the kinetic energy of the alpha particle is larger than the potential energy, and inside this to the left of this point, the potential energy of the alpha particle is larger than the kinetic energy. So that's what we get from this picture of alpha decay from the point of view of quantum mechanics. Now we have to evaluate certain things pertaining to alpha decay, and we are not going to derive this as such, but for a barrier, for a rectangular potential barrier, here we can see that the barrier is not rectangular, it is tapering like this. But for a rectangular barrier, we know how to evaluate the transmission probability of a particle using quantum mechanics, and that is approximately e raised to minus 2k2 times L, where L is the width of the barrier and k is this quantity, root of 2m into u minus e by h cross. This we have learned already in quantum mechanics. So, but here the okay, from this equation, if you take log on both sides, you have something like this. You get minus 2k2 times L. But here the difference is, here your L, that is the width of the barrier, it's not constant, right? It's not a rectangular shaped barrier. So what you do, you just divide this into small rectangle shaped areas, and then you integrate. Okay, the barrier width, you just divide this entire barrier into small rectangle shaped areas and you integrate from where to where, from r0 to r. Okay, so that is what we've done here. Log t would be minus 2 times k2 r from r0 to r, where r is the radius of the nucleus and capital R is the distance from its center at which u equal to e. See, beyond that point, capital R, the kinetic energy is of course greater than the potential energy. So the alpha particle will have permanently escaped from the nucleus. So just consider this. This is the region where, see, this region from R0 to this particular R, this is the region where the alpha particle doesn't have enough energy to cross the barrier. So this portion of the barrier, it just has to tunnel through. So this is what we consider as the barrier width. Beyond this point, of course, the kinetic energy is greater than the potential energy and the alpha particle will be escaping from the nucleus. So this portion of the barrier is what the alpha particle needs to cross, but the barrier shape, it is not a rectangular shaped barrier. So that is why you cannot take the width as L, a constant value. You just divide this into small rectangle shaped areas and you integrate from R0 to R. And you write this integral like this. The potential energy of the alpha particle is of course given by this equation, 2Zd square by 4 pi epsilon 0 r. Zd is the nuclear charge minus the alpha particle charge of 2e. Okay, and k is given like this, and if you substitute the value of u in this equation, this is what you get. Now we know that at the point when distance becomes equal to capital R, u becomes equal to e, isn't it? So what you do is you multiply and divide with one capital R here. So here you will get a term involving e. Here also you have a term involving e. So e can be taken common, and the rest of the terms can be written like this. So the capital R, which is multiplied in the numerator, remains like that, and in the denominator there will be a small r. E in this term and e in this term is taken common and it is under the root. So you will have root of 2me by h cross square times root of capital R by small r minus 1. Okay. And that is k2, and you have to plug in the value of k2 and you have to integrate this. And this integral, it has several steps. Actually, we are not going to go into the details of how this integration is done. I shall provide you material for that if you are interested. And here, on integrating this, this is what you get. cos inverse this quantity minus such a term. Now, because the potential barrier is relatively wide and you can take that R is much greater than R0, you can make an approximation for cos inverse this term as pi by 2 minus like this. And when R is much greater than R0, your R0 by R would be negligibly small and this term can be approximated as 1. So log T would be changing to this quantity on making these approximations. We already know capital R is given like this, and if you put in that value, your log T will turn out to be like this. And these are all constant values, right? E, M, H cross, pi, epsilon 0, etc. When you put all those values, you will get something like this: 2.97 Z raised to half R0 raised to half minus all these constants plugged in, 3.95 Z e raised to minus half. Okay. Here E is the alpha particle kinetic energy which is expressed in MeV, this E. R0 is the nuclear radius which is expressed in femtometer, R0. And Z is the atomic number of the nucleus minus the alpha particle. Okay. And since we know log to the base 10 sum A is log to the base 10 E times log A, which is equal to 0.4343 log A, we can write in terms of log to the base 10 T, the transmission probability, as like this. And from our previous equations, the decay constant is given by lambda is nu times T, and you get instead of nu you can put it as V by 2R0 times T, and you get an expression for your lambda, log lambda, and log this quantity and this quantity. This is instead of T. Okay, so you're taking logarithm on both sides of this equation. Taking logarithm on both sides of this equation, you get log lambda is log this quantity plus log T. Okay, log T is this. So that's what you have written here. V is the alpha particle velocity. E is the energy in MeV. R0 is the radius in femtometer. Z is the atomic number of the daughter nucleus. And if we are attempting a plot of log Z versus Z raised to minus half, we will get a straight line. Okay. So this is what we can get a lot of information from this plot also. Equation 1214 predicts that decay constant and hence half-life is strongly related to alpha particle energy E. And some interesting data is that the slowest decay is that of 232 thorium. Its half-life is 1.3 into 10 raised to 10 years. And the fastest decay happening is for polonium, whose half-life is 10 raised to minus 7 seconds. So you can just see the variation in half-lives. But if you look at the alpha particle energies, the alpha particle energy of thorium is only half that of the alpha particle energy of alpha particle produced in the decay of polonium. Okay. So you can get such information also from this equation. Thank you.